In this module, we discuss how we can compare segments when the dependent variable is quantitative in nature, for example, expenditure on the product category. We will consider only the case where there are two segments. The case with more than two segments will be discussed in a later module. There are two types of tests you need to learn about. The first is a two-sample test, also known as an independent samples test, which is used to test if two populations or groups or segments are different from each other on some variable. The question we are asking is the mean for population 1 equal to the mean for population 2? Some examples of this might be if we ask whether men and women drink different amounts of coffee or spend different amounts on athletic shoes. The second type of test involving a difference of means is a paired t-test, also known as a related samples test. This is used to test if the mean changes in a given population. The question we are asking here is the mean for one set of observations the same as the mean of a second set of observations from the same source? Some examples. Does blood pressure in a group of patients change after taking medication? Here the source of the data is a group of patients. Or we could ask, do sales in a store change after a price cut? Here the source is a set of stores. Yet another example. Does preference for a brand differ from preference for another brand in a group of consumers? Here the source is a group of consumers. Let's look first at the two-sample t-test. The basic idea is that there are two separate samples drawn from two different populations, and we test if the means from the two populations are different. The null hypothesis is that the means of the populations are equal, that is, there is no difference in the population means. The variances of the two populations are unknown, but in order to test whether the means are different, you have to assume either that the variances of the two populations are equal or that they are unequal. This assumption is required because part of the formula for the test depends on what you assume. If you assume equal variances, you can conduct an ANOVA test instead because it gives you the same results. But if you assume unequal variances, you only have the option of doing this t-test. The test statistic is a t-statistic if the sample size in either group is less than 30. If both samples are at least 30 in size, it is distributed as a z-statistic. The formulas look a bit ugly, and I'm not going to repeat them here since you can look them up, but you don't need to know them because Excel comes to the rescue and does the test for you. You just need to have the data in two separate columns, as we'll see. We're going to look at an example where we asked two groups, men and women, how much they agreed or disagreed with the statement, natural food is healthier. The values are from 1 to 5, where 1 means strongly disagree and 5 means strongly agree. This is what the data need to look like for Excel to do its magic. Each group's responses are in a separate column. You do not need to have an equal number of people in each group, as we'll see in the next slide. After you click on the data analysis icon in Excel, select the option t-test two-sample assuming unequal variances. This box will then pop up. Fill in the range for the two variables, check the box for labels and indicate where you want the output. Let's look at the results. Keep in mind that the variable we are comparing is agreement with the statement about natural food. A higher number means more agreement and a lower number means more disagreement. This is important because you need to know this in order to interpret the results. Here's what the Excel output looks like. At the top is the type of test, in this case a two-sample t-test with unequal variances. Next, it shows the populations or groups being compared, in this case men and women. You can see that the sample size for the two groups is not the same. There are more men than women in the sample. The next important piece of information is the mean for each group. This is where you need to remember what those numbers mean. A higher number means more agreement with the statement. So based just on the means, we would say that women are more likely to agree that natural food is healthier since their mean is 4.14 compared to 3.87 for men. But before we can jump to that conclusion, we need to check that the means are significantly different based on the p-value for the test. Here, the p-value is a very small number and certainly less than 0.05, which is our cutoff, that is, our alpha value. So should we conclude that the means are different? I'm going to pause for a bit while you think about it. Write down what you think. Are the means different or are they the same? Different, same. Time's up. What did you write down? If you wrote that the means are different, you are right. The test is highly significant since the p-value is less than 0.05. The last step is to write down what you just concluded. That is, women are more likely than men to agree that natural food is healthier. Simply saying that the means are different without explaining how they are different is not enough. Here's an assignment to test your understanding of how to do this test. Download the Excel file MPG data, which has data on miles per gallon measurements for 79 Japanese cars and 249 US cars. Conduct a two-sample t-test to determine if the mean MPG is different for the two sets of cars. Assume that variance is unequal in the two populations. What do you conclude from the results of your test? Here are some tips that can help you with this assignment. Use the data analysis add-in for Excel and choose the two-sample t-test assuming unequal variances option. In the output, look at the p-value for the two-tailed test. If you like, you can view a video on how to do this test in Excel. The next test we'll look at concerning the mean is the paired t-test. This also compares two samples, although the samples in this case are not drawn from different populations. The data here come from samples that are related to each other in some way. For example, they could be before and after measurements of people who have taken some medication, or the weight before and after going on a diet. In a marketing context, it could be sales from a set of stores before and after a price change. These are all examples of paired observations, that is, observations that come in pairs. We use what's called a paired t-test. The basic idea is very simple. We take the difference di of the two measurements and test whether the average difference is 0. So our null hypothesis is that the average d bar equals 0 and the alternative is that it is not equal to 0. In this case, unlike the previous test, you must have an equal number of observations in both samples. If the sample size n for each set of readings is less than 30, this is a t-test. If n equals 30 or more, the test is a z-test. We're going to look at an example where we compare blood pressure readings among a set of patients before and after taking medication. A lower number is a better outcome for the patient. Again, this is what the data need to look like for Excel. Each set of readings is in a separate column. But unlike the previous test, the data in each row come from the same patient. Since you need to have before and after readings for each patient, the number of observations in each column have to be equal. After you click on the data analysis icon in Excel, select the option t-test paired two-sample for means. This box will then pop up. Fill in the range for the two variables, check the box for labels, and indicate where you want the output. So let's look at the results. Keep in mind that the variable we are comparing is blood pressure. A higher number means higher blood pressure, which is a worse outcome for the patient. You will need to know this in order to interpret the results. Here's what the Excel output looks like. At the top is the type of test, in this case a paired two-sample t-test for means. Next, it shows the observations being compared, in this case before and after measurements. You can see that the sample size for the two sets of readings is the same. The next important piece of information is the mean for each set of data. Based on the means, blood pressure after the medication is 132.3, lower than 134.3 before the medication, even though the difference is small. In that sense, we could say the medication has had an effect. But before we can jump to that conclusion, we need to check that the means are significantly different based on the p-value for the test. Here the p-value is a very small number and certainly less than 0.05, which is our cutoff, that is our alpha value. So should we conclude that the means are different? Of course. The test is highly significant and you can conclude that the systolic blood pressure is lower after the medication, so it did have an effect. The last step, as before, is to write down what you just concluded. Simply saying that the means are different without explaining how they are different is not enough. Here's an assignment to test your understanding of how to do this test. Download the Excel file Student Data, which shows student scores on a test before and after viewing a tutorial on the material. Conduct a paired t-test to determine if the mean score is different for the two sets of observations. What do you conclude from the results of your test? Here are some tips that can help you with this assignment. Use the data analysis add-in for Excel and choose t-test paired two-sample for means option. In the output, look at the p-value for the two-tailed test. If you like, you can view a video on how to do this test in Excel.